So we are starting from the one we have the at the fairground. Okay, continuing with the same topic 17 and 17.4. I'm pasting that right now on the board. Yeah, it's loading. One page is just pasted on the board, and here is the second one I'm pasting right now.
Yeah, got it. Yeah, see it.
Okay, this is the second page. Just loading now. I will paste all the pages one time and then we will do that all together.
Okay.
Okay. And now the questions on this one. This is the last topic of chapter number 17, 17.4. And then we are, the next after this one, we are doing the exercise questions of this one.
Okay. Yeah.
The summary questions and the practice question of this chapter.
Okay.
Okay. Let's just start from the beginning of this one. So at the fairground, like we are talking about the circular motions over here, okay? And then let's just talk about many of the rides at the fairgrounds are the amusement park, you know, take people around in circle, right? We have seen that
Yeah.
one, like then over there, they're just taking the people in the round circle. So some examples are analyzed below. We will just see that one in example below. So it's worth remembering that the centripetal acceleration, that's the important thing, value of more than 2 to 3 G can be dangerous for the average person, right? If we cross the 2 to 3 G, G means into the gravitational acceleration, if we time that, right? So then that could be dangerous for per person and that circulating wheel.
Okay. Okay.
So then we have the big dipper. Like, you know, if you are moving, it's like this kind of a curve path, like at the very bottom of this one, we are discussing about that one. So it's called that one as a big dipper. Okay. So the ride that takes you at a high speed through a big dip pushes you into your seats as you pass through a dip, right? If you pass like this kind of a curve path, your speed would be maximum. Then what will happen? Your seat, as you pass through the dip, the difference between the support force and you, like your weight and the support force, you can see this one over in the figure. Your weight is pulling you downward, and then there is a support force upward against the weight, right?
Yep. Support force being the one that keeps you up.
Yes, which is act as a centripetal force. That whenever anything's rotate in a circle, there is a centripetal force act on that object, which rotate that one around the circle, and it's always directed toward the center of that object, right? It's the same going down over here in the dipping case. If it's at that bottom where the speed would be maximum, its weight is pulling it downward, and the centripetal force it's opposing that one, which is always toward the center of that curvature or that dip. Okay.
Okay.
So at the bottom of the dip, the support force S on U is vertically upward. You can see this one over here, as shown in figure 1. So therefore, for a speed V at the bottom of the dip, the radius of the curvature is R.
Yeah. So radius being this part here.
Yes, yeah, definitely. Over here, it is this part. Curvature's radius. And then we have the formula for that one. S is, we know that the support force, which is pushing it toward the center against that of the weight, minus mg. We already know that when the object is at this dipped point, the weight is pulling it downward and the support force is acting toward the center. So they are opposite of each other over here at this dip point, right? So then we write it down S minus mg, which is equals to mv square. right? The object is moving in that circle just because of that force, and which is equals to the centripetal force, right?
Yeah.
F, which is equals to mv square divided by r. F, we know that we have two forces, which is the weight downward and the support force toward the center. So we, in place of just S, we write it down S minus mg, which is equals to mv square divided by r. Okay.
So force is S minus mg in this case.
Yes, in this case, two forces there. One is the support force pulling it toward the center, and the other is weight, which is pulling it outward. So the support force, if you just find out the support force, then it would be S is equals to mg plus mv square divided by r. We just rearrange, we take that mg toward the other side and becomes plus mg.
Okay.
Okay, so then the extra force you experience due to the circular motion is mv square divided by r. Okay.